starting a new recording so that we have two different videos. So the next topic that we have is thermal properties of matter. We had in our syllabus the thermal properties in our O-level syllabus. Then in the AS level, it was altogether not available. It was not taught at all. And then in the AS, we once again have it. What just happened? Why do I have so many desktops? What is this? Okay, now to go here. Okay. So for the thermal properties that we're gonna see, we're gonna have to remember stuff that we have learned in our O-level syllabus. Then there'll be some additional stuffs over here as well. Couple of things to understand: that what do we mean by thermal energy? First, what is the key expression of what do we mean by thermal energy? Thermal energy is sometimes also referred to as internal energy. It is also called internal energy. It is defined as the sum of macroscopic, potential, and kinetic energies of the particles of an object. এটা হচ্ছে internal energy basic definition. The reason we define it as macroscopic, potential, and kinetic energies because this actually means the individual energy that any object in any of its state can possibly have. Normally, in our regular life scenarios, objects can have three different states: solid, liquid, gas. There is another fourth state of object, which is called plasma, which is basically a superheated condition of objects where the entire atomic structure is actually broken down because of the total amount of energy of the system. It's actually a huge lump of free nucleus and electrons and protons and other things. So that's what we call a plasma. We're not going to learn about plasma in our A2 level, so plasma is off limits. So if you consider solid, liquid, and gas, in solid, the particles are pretty much stuck in their original position. All that they can move is vibration. So, and they also have some potential energy with respect to each other because of the attraction forces, strong attraction forces between the particles. So the total energy that you could possibly have that an object have stored can be said to be the internal energy. In liquid, particles do have significant intermolecular forces which cause them to have a fixed volume, but liquid state does not have a fixed shape. They can actually move from one location to another location, which we call translation. Translation means actually moving from one location to another location, whereas vibration means moving about one equilibrium position. This is the two different type of movement that you are going to learn. Vibration is moving about a fixed equilibrium position or a defined equilibrium position. I'm not going to use the word fixed because that might be a bit confusing. Moving about defined equilibrium position is what we call vibration, and translation means actually moving from one position to another is what we call to be translation. Most of our topic for our thermal energy chapter is gonna go for gaseous substances. We're gonna see a lot of conversion and dependency for gaseous substances. Gaseous substances practically has both potential energy and kinetic energy in real cases, but the amount of potential energy that they have between them is actually very small compared to the kinetic energy that they have, because gaseous substance doesn't have any fixed volume. They occupy the space in any container that we put them in. So this actually brings up the idea that particles can be really far apart. The average intermolecular spacing or average interparticular distance can be extremely large. So the attraction force between two particles can be very nominal, and potential energy actually rises from the effect whenever multiple particles within an object has some intermolecular or interparticular attraction between them, that leads to potential energy growth. And if particles don't have that to a significant value, we can consider the potential energy to be negligible. And in an ideal case, ideal cases are actually always imaginary, which are a very simplified version of a much too complicated scenario. You know how the our ideal is actually applicable. For example, uh, uh, how can I put the concept for an ideal? For example, ideal gas. There's a thing we're going to learn about ideal gas. Ideal gas is a close approximation of real gas, but with much less complexity. We're going to learn about that as well. Before I go into that, I'd like to discuss the first law of thermodynamics. There are three laws of thermodynamics. We are not going to learn in our syllabus about the second law of thermodynamics. I can tell you the zeroth law of thermodynamics, which might sound a bit ridiculous, but there is a defined law for that. And we're going to also learn about the the first law of thermodynamics that is also within our discussion content. Okay, that's one thing. Before I move into the actual subject content, I'd like to put some effort to define some very basic quantities which are required for this chapter. You might have actually come across these definitions, but this is the point where you need to distinguish between different values. What do we mean by absolute scale of temperature? Absolute scale of temperature is the Kelvin scale of temperature. The Kelvin scale of temperature actually came into existence when uh, uh, scientist Charles, I don't know his full name, he was doing some experiment with the gases. But he found out that if we have different gases or same gases with different volume, and we change the temperature. For example, if we have the theta in degrees Celsius on the x-axis and the volume of a certain amount of gas on the y-axis, and if we change the temperature of these things, he found out that one sample of gas always gave lines like these. So they were somewhat like these. And it was eventually found out that if we pull back all of these lines on the left side, they were apparently crossing on the x-axis at one single point. And this was true for all the gases, no matter how much of gas that you start with, no matter how many moles of gas that you start with, no matter which gas did you choose, all gases showed this behavior to have one single cross point on the x-axis. This point is what we define as 0 Kelvin. What is the value of 0 Kelvin for degree Celsius scale? I'm going to get to that number just after a while, because I need to differentiate between you in your head for two different numbers. So this is 1 Kelvin. Now scientists wanted to define how much should, and then they defined this is a 0 Kelvin. And from this point, they defined the Kelvin scale, and they designed the Kelvin scale for the sake of simplicity, that 1 degree Celsius temperature change would mean 1 Kelvin temperature change. So basically the amount of change of temperature will remain the same. So it means somewhat what you have learned in your O levels, that at 0 Kelvin, the temperature is minus 273 degrees Celsius. At 0 degrees Celsius, the Kelvin is 273 Kelvin. At the boiling temperature of boiling temperature of water, this axis is not drawn to scale. I have drawn minus 270 over here, drawing 100 over pretty much at the same distance. But what I'm trying to show you, at 100 degrees Celsius, this is 373, so on and so forth. But there is a bit more difference after these digits. There comes some decimal points over here, which are required for you to know precisely. 1 Kelvin temperature is defined as 1 Kelvin temperature is defined as 1 by 273.15 part of the temperature of triple point of water. Now, what is triple point of water? You do not have the whole discussion of triple point of water in your syllabus, but just to make sense, I'm going to tell you what this is. Let me show you the definition of 1 Kelvin from Wikipedia first, so that we uh, have no confusion about that. Wow. Oh, I don't know what I did. I'm trying to type something within my keyboard, and my keyboard is giving me, allowing me not to type. It is minimizing certain stuffs. What is this? Definition of 1 Kelvin. Okay. Oh, sorry, 123.273.16. I messed up. Okay, this is the part that you really want to have a good look. 1 Kelvin is formally defined as 1 by 273.16 of the thermodynamic temperature of the triple point of pure water. So there are a lot of variables over here. Triple point of pure water. A temperature of 273.15 Kelvin is corresponds to 0 degrees Celsius. So there are two different values over here. You have to understand this thing. This is the part that I really want you to understand. 0 degrees Celsius is perfectly 273.15 Kelvin, whereas 1 Kelvin is 273.16 part of the temperature of triple point of pure water. I forgot to write pure, so might as well add that. This is the definition of 1 Kelvin. Now, if you wonder what is triple point, let me give you an idea. One of the concepts that I wanted to grab is that water has three stages, three state: solid, liquid, gas. We call them ice, water, and steam. But gaseous water can also be vapor, which is a pretty interesting state of water. I mean, if you come to think about it, that the boiling temperature of water is 100 degrees Celsius under 1 atmospheric pressure, which means if you want to boil some water, you have to reach the temperature of liquid water to 100 degrees Celsius. At that point, the water will start to boil. However, water can self-evaporate at a temperature much lower than 100 degrees Celsius. If you have some water spread around with one on a floor, on a surface, after a while, you'll see that water has gone away. The reason the water goes away is because the atmosphere can absorb that water in its gases form, which we call vapor. Now, the temperature of the atmosphere is not necessarily even close to 100 degrees Celsius, but the atmosphere does contain water vapor in gaseous form, which should give you the idea that water can also exist in gaseous form at temperature lower than 100 degrees Celsius. This is the part that I want you to understand. That if you want to boil water under 1 atmospheric pressure, you have to reach temperature 100 degrees Celsius. That's for boiling. But it is possible for water to exist at its gaseous state at temperatures lower than 100 degrees Celsius. This is the important part. Why is this important? Because this gives us an idea that the gaseous state not only depends upon temperature, it is also equally dependent on pressure. Any gaseous object has these two variables which controls its fate. One is pressure, the other one is temperature. So if we take these two variables and try to plot a graph of a certain amount of water for different values of pressures and temperature, we are gonna get a figure which we call the phase diagram. So I can try to show you that. Phase diagram of water. Let's have a look. Yes. This is the phase diagram of water. How big is this picture? Small. Can we get a bit bigger picture? Actually, this is a really good picture from Wikipedia. Yeah, nice one. Open image in new tab. So we don't actually have to understand all the different parts of it, but what I wanted to understand that this yellow region represents gaseous water. This green region represents liquid water. All of this blue region represents solid water or ice. So you can see on the y-axis we have pressure. The pressure scale is actually in this case exponential scale. You should see 1 Pascal, 10 Pascal, 100 Pascal, 1000 Pascal, 10,000 Pascal, 100,000 Pascal, 100,000 Pascal, 1 megapascal, 1,000 Pascal, then 10 megapascal, 100 megapascal. So this is an exponential scale, or sometimes we call it logarithmic scale. So if we have 1 Pascal at 1 Pascal, atmospheric pressure is about 10 to the power 5 Pascal. Atmospheric pressure is about 10 to the power 5 Pascal. So which means atmospheric pressure is somewhere around here. Freezing point at 1 atmospheric pressure is 273.15 Kelvin at 101,325 kilopascal. This is the typical room temperature that we have. Boiling point at 1 atmospheric pressure is this thing. If we shift this observation line, we're gonna have the freezing point of water pretty much fixed up to 10 megapascal, but beyond 10 megapascal, water can be liquid even below 0 degrees Celsius. But this picture actually shows you that at any combination of pressure and temperature, it shows you the state of water. So this is actually a much more bigger view. This also has all the individual atomic arrangement of the water molecules. This is orthorhombic, this is hexagonal, and these are all different type of water stages for research purposes. We don't have to know it to that detail level. The simple figure that is helpful for us is this one. So what you can see, this is what we call the triple point. It means there exists a certain combination of pressure and temperature at which all three states of water can coexist. Coexist means that you can have liquid water, gaseous water, and solid water, all three at the same value of pressure and temperature. This is basically what we call the triple point. Now, you might wonder, isn't that possible in room temperature? I mean, I can pull out ice from the refrigerator and I can have liquid water beside it, and then I can have gas in the atmosphere. The answer is no. Under 1 atmospheric pressure, ice can only exist at 0 degrees Celsius. If you have 1 atmospheric pressure, 0 degrees Celsius is the transition point between liquid water and solid ice, which is shown in this figure. At 1 atmospheric pressure, this is the temperature for the transition between water and ice. And this is the temperature for the transition between liquid and gas. However, at 1 atmospheric pressure, you can see at temperatures from 0 to 100 degrees Celsius, water can remain at gaseous state. There is a small of this gaseous state. This is the scenario where we have all the atmospheric vapor existing over here, which means you cannot have solid ice at temperature above 0 degrees Celsius in 1 atmospheric pressure. So you can have them coexisting side by you can have them side by side, but the individual temperature of those specimens would not be same. There is only one specific point of combination of pressure, temperature, where all the three objects can coexist. This is basically this point. This is what we call the solid, liquid, gas, vapor triple point. This is a very low temperature. This is much smaller than 1 kilopascal, a bit higher. Somewhere within, I think it's 600 Pascal or something. If I forgot, 600 or 700 Pascal, something like that. Yeah, 611.657 Pascal. Yeah. So this temperature is 273.16 Kelvin. Have a look. This is important. I'll zoom in. This temperature is 273.16 Kelvin, whereas the transitions temperature for ice to water or water to ice at under atmospheric pressure is 270.15 Kelvin. So you should remember this decimal point. These are important information for your A2 level, and you shouldn't forget that. So what I'm trying to show you over here is that 1 Kelvin is defined as 1 by 273.16 part of the temperature of triple point of pure water. What is triple point of pure water? It is the combination of pressure and temperature at which pure water can coexist in all of its states, solid, liquid, and gas. And 0 degrees Celsius is not this exact temperature. This is 0.01 Kelvin less. 0 degrees Celsius is 273.15 Kelvin. সো এই দুটো ইনফরমেশন যাতে আমাদের ভুল না হয়, ইটস ইম্পর্টেন্ট। The next thing that I'm going to discuss, and then I will call it a day, that is, if we do some work on a system, the system's energy get increased. If a system does some work, then system's energy get decreased. A very simple example can be shown over here. For example, if we have a horizontal cylinder that is fixed up, that is attached with some frictionless piston, and let's say we have some gas, not necessarily atmospheric gas, some gas confined within this chamber. Let's say the amount of pressure over here is 1 atmospheric pressure. So we have nothing complicated. We have 1 atmospheric pressure. So currently, if the piston is at an equilibrium state, this actually means that the pressure from this side is also 1 atmospheric pressure. The pressure from this side is also 1 atmospheric pressure. That's why the forces are equal, because force equals to pressure into area. So within the same area, they are applying the same amount of force. That's why you have the piston fixed in a position. Now, if I start to apply energy, let's say if I start to provide heat in this cylinder, which is going to heat up the gas molecule over here, what's going to happen? They are going to start to collide with bigger amount of energies. So they're going to collide more often, and they're going to collide with bigger force, resulting in an increase in pressure. If we have this end of the piston free to move, then simply this piston is going to start to slide to the right, because the inside pressure is going to rise. This is going to produce a bigger force from the left side, and this will push the piston out. Now, what I need to understand, in this process, heat energy was fed into the system. This is the input energy to the gaseous system. And in the process for the piston to move out, this piston actually had to push out the atmospheric molecules that used to exist over in this position. Let's say if the piston eventually comes out to this position, let's say this is the new position of the piston, it means this much air volume had to be pushed out for the piston to move by. That is actually work. You are moving mass by the application of force, This is important. Why? Because whenever we are doing this by applying some force, we are doing some work, that actually leads to the idea of work done. In this case, the piston is doing work, or in other words, the gas is doing work on the system, on the atmosphere. So what is happening? Heat energy is going in, work done is coming out. I'm giving them plus up and minus to give you an idea of internal energy. So if we want to give an if I want to give you an idea that total amount of change of internal energy is usually represented by the symbol capital U. Change in internal energy can be given by delta U, is given by the addition of delta Q in this case minus the work done against atmosphere, because in this case work was done against the atmosphere. This is the scenario. The other thing that can happen is that we can apply the heat, and maybe with some physical force from the outside, we're going to push in the cylinder as well. So we're going to do both. In that case, the increase of delta U would be provided from heat supplied. It will be also provided by work done. In that case, both of them would be added up together. This concept is basically what we call the first law of thermodynamics, which we're going to pick up in more detailed format in our next class. তোমরা ওয়ার্কশিট যারা করো নাই ওয়ার্কশিটগুলি করো, আর যাদের ওয়ার্কশিট করা হয়ে গেছে, try to do some problems from the recent years and start to go backwards. So download some question papers from the websites and attempt those problems. And if you have any questions, আমাকে নেক্সট ক্লাসে দেখাইতে পারি স্যার এই ইয়ারে এত নাম্বার কোশ্চেন আছে, আমি কোশ্চেন বুঝি নাই বা পারি নাই বা এটা করতে পারতেছে বা মার্ক স্কিম মেক সেন্স করতেছে না, I'll be glad to discuss those problems with you. Thank you very much. Assalamu alaikum.